Okay, so this video is to finish or to complete a video I recorded a few days ago, where I didn't end up recording the last half. So apparently, for like 10, 15 minutes, I was just speaking to a webcam that wasn't recording me at all. So what it seems like it happened is you see this image here, right? That image wasn't on my slide. So I paused it to go find that image and paste it in. And what I think happened is I started speaking and I didn't hit unpause. So I apologize that the last few minutes of that lecture are missing. I'll post it in the appropriate day so that it will be complete there. Okay. So we were talking about star formation, how stars form. We had that interstellar gas cloud, and something triggered instabilities or clumping that caused matter to collapse. And these gas clouds started to fragment, and they got smaller and smaller. And then you had these massive gas clouds split into hundreds or thousands of fragments. And then these fragments continue to collapse. And as gravity pulled them inwards, they started to acquire a rotation, a spin. And as they collapsed smaller and smaller, just like a figure skater skating on ice, when a figure skater begins to spin and they pull their arms in, they start spinning faster and faster. So as this gas cloud that's large is slowly rotating, as it compresses and gets smaller and smaller, it spins faster and faster. But as it's spinning, just like a how would you say, not a baker who makes the pizza. It's not a baker, right? The gentleman or the woman or whoever at the pizzeria who's flipping the dough, when they spin the dough up in the air to make the flat pizza, right? The dough spreads out, right? When the protostellar disk, sorry, when the gas cloud starts spinning, right, it starts to spread out, making a disk. It is from this disk that we form the planets and all that we find in a solar system. But at the center, we have the protostar. All that hydrogen, gas, and dust is collapsing under gravity. It starts getting hotter and hotter and hotter. And as it gets hotter and hotter and hotter, it starts becoming luminous. It starts giving off light. Okay? Eventually, we reach a point where we begin nuclear fusion and we become a star. So these images here, right, this is in the visible spectrum, this image. Right? These images here I don't think are in the visible spectrum. Right? So these parts here are artist renditions of what a protostar would look like, proto being early. And you see its gas cloud. Not just gas cloud, it's protostellar disk. This is what we're seeing here. Right? This is looking top down. We are seeing a protostar, and then we are seeing this disk around it. And here we see protostars being looked on, edge on. So my fist is the star, and we're looking edge on. These dark bands represent the disk that is blocking light. Okay? So we have visual confirmation seen here, looking top down, and here looking edge on to the existence of these protostellar disks and these protostars. So, protostar. As the protostar starts evolving, it keeps shrinking. And as it keeps shrinking, right, the temperature inside, and where can I go? I'll hang out here. The temperature inside gets hotter and hotter, the density increases, and we reach 10 million degrees Kelvin. We're not quite at nuclear fusion yet. But protostars, very bright. They tend to be very luminous. They're brighter than the main sequence star they will normally become because they're large. Their radius is 1,000 times the radius of not 1,000, is 100 times the radius of the sun. So it's not really a nuclear fusion yet. It's super hot, okay, super hot, but because it's so big, right, 100 times bigger than our sun, okay, it is very luminous. Next step, once a protostar becomes a hydrogen-burning star, once nuclear fusion starts, okay, a strong stellar wind forms. So we get a stellar wind is the expulsion of all sorts of subatomic and atomic-sized particles, generally from the poles along the axis of rotation, so from the north and south. So what we see in the protostar, it's spinning in a disk, right? So we got the protostar spinning in the center. We got the protostar spinning in the center. Around it, and I can't stay in the center, around it is a disk, but out of the star, from the top and bottom, there will be outflows of the stellar wind, right? So it'll be charged particles flowing out at tremendous velocity. Okay, so we've seen evidence of this phase where we have these jets coming out of the protostar, and this phase of the star's life is known as the T Tauri phase. Okay, so here we can see a very simple Hertzsprung-Russell diagram. We got the main sequence star, right? The T Tauri stars, right? Those are protostars. They have not yet reached the main sequence, but they will. Okay, let's follow along with this diagram here. So we have the protostar assembles from a collapsing cloud fragment and is concealed behind a shroud of dusty gas. Right? The protostar shrinks, so gravity's pulling it in. It starts getting hot. Right? So this gravitational energy becomes heat. 3, surface temperatures rise when radiation becomes dominant mode of energy flow within this protostar. 1 second, that is my wife. Sorry about that. It's a little late here. It's 4 o'clock. So yeah, she's just wondering when I'm coming home. Okay, so when we get here, we're main sequence, right? That protostar is now a star. It's going through nuclear fusion, right? So it's no longer a protostar. It's actually a main sequence star. Okay, so stage 5, right? Protostar. Sorry. Yeah, sorry. So protostar evolution, right? That pathway, if we go back to the Hertzsprung-Russell diagram, going from the protostar or the T Tauri star to the main sequence, following along that path in its evolutionary pathway, the process of going from a T Tauri protostar to a main sequence star, we call that the Hayashi tract. Right? So it's a Japanese astronomer. So we have our protostar, and it goes through the Hayashi contraction. So that's when it continues to shrink down and becomes a star proper. It starts going through nuclear fusion. So in the Hayashi tract, right, here's our protostar. These would be our T Tauri stars. This is them going to the main sequence. Right, the protostar approaches main sequence, shrinks to 10 times the size of the sun, and its luminosity decreases to 10 times that of the sun. So the protostar is moving down to become a main sequence star. Eventually, if it's a sun-sized star, it'll be just exactly like our sun. In the Hayashi contraction, right, here we can see 2 different arrows. Right? Smaller stars will become, smaller protostars will become smaller main sequence stars. Bigger protostars will become bigger main sequence stars, right? The supermassive ones will end up here being blue giants, right? The smaller ones, right, will end up here being red dwarfs. Where can I move to? I'm not in the way. That looks good. Okay, so And you can't see my hands. I'm being expressive, but it's not capturing all of me. Okay. So we had the T-Tari phase, right? The protostar. It goes through Hayashi contraction, and now it's a main sequence star. So we have stage 6, right? So this is kind of stage 6, the protostar and stage 6 and 7. They're not separate, disparate events, right? They're one logical flow. It's one progression. So they're not distinct, separate phases. Right? It's a logical progression through. Let's move me over here. So stage 6, the newborn star. Star has contracted, internal temperature has reached 10 million Kelvin, and nuclear fusion is starting. So this star is virtually on the main sequence now. It's virtually beginning its proper star life. Star contracts a little more, get a little more contraction. So this stage 6 here, newborn star, it's actually kind of even labeled a little wrong. I would still call it like a late protostar or a late T-Tari protostar. Right? We get a little more contraction, gravity pulls it in a little more, temperature increases due to pressure and gravity, and we now reach 50 million Kelvin. We begin nuclear fusion. Right? The star is fully burning hydrogen at its core. Okay? So it's fully burning hydrogen at its core. It's a proper star. A star the size of our sun, its surface temperature would be 6,000 Kelvin. Bigger stars, right, will be hotter. Smaller stars will be cooler. And at this point, no matter what size the star is, no matter how hot it is, if it's a very hot type O, giant blue star, or a cooler red star, right? It doesn't matter. The same thing is happening. You've got the inward force of gravity pulling all the gases and everything in, right? Because the closer matter is together, the stronger the force of gravity. So you've got billions and billions and billions of tons of gas being compressed, and they're all pulling on each other. So we've got a strong source of gravity, right? And that should keep compressing and pulling in eventually till you reach a singularity or a black hole. But we've got nuclear fusion happening. Nuclear fusion is putting heat and pressure outwards. So we've got gravity coming in. We've got nuclear fusion and heat and energy going outwards. And during the main sequence, the inward crush of gravity and the outward push of nuclear fusion are equal. They're balanced. Okay? So they're balanced. Because we're balanced, we now have a sphere, right? If they were out of balance and there was more gravity, the sphere would collapse. If they were out of balance and there was more nuclear fusion, the star would expand and grow and eventually possibly dissipate. But at this point in the main sequence, gravity crushing in, nuclear fusion pushing out is balanced, and you have a perfect sphere like our sun floating out in space in the cosmos and providing energy for all life on our planet and powering our weather and whatnot, and all that good stuff. So a star like our sun, so our sun is a relatively small star, right? So a little smaller than a middling star. It should have enough hydrogen in its core to burn on the main sequence for about 10 billion years. Our star, Sol, or the sun, right, has existed for about 5 billion years, so it's about halfway through its main sequence life. Right? In 5 billion years, after we are gone and we are dust, our star will start doing something different, which the future lectures, which I've already recorded because I'm going back in time and recording this one, will explain. So please note that this whole process of star formation takes about 50 million years, 1% of the star's lifetime. So going from a gas cloud to a star, main sequence, about 1% of the star's life for our sun. Okay? Then it's going to spend 10 billion years burning as a yellow star. Right? After those 10 billion years have passed, red giant, right, then planetary nebula, then white dwarf, then black dwarf. Okay, next thing here, this note, the time required for a star formation is strongly correlated to the mass of the cloud. The bigger the cloud that forms the star, right, the more gravity potential there is, the faster it can collapse and the bigger star it will become. So massive stars that become the massive blue giants, right, their formation might only take 1,000,000 years versus 50 million years for our sun, because there's so much gravity in that massive cloud that never fragmented. Next point worthy of noting, right? Stars that are 0.08 or 8% the mass of our sun, okay? If a star is, or if a gas cloud is 8% less than the mass of the cloud that became our sun, right? It's too small. It will never become a true star. It will never begin nuclear fusion. Okay? So a gas cloud that is 8% the mass of our sun will never become a star. It's too small, right? It can start to collapse and gravity can start to pull it in and it will get hot, right? It will heat up, but it will never reach the point where it's extremely hot and it'll begin nuclear fusion, right? It will become what we call a brown dwarf star, right? Actually, I wouldn't even call it a dwarf star. Let's just say the brown dwarf, right? Small, faint, and relatively cool in comparison to other stars, right? It'll probably be hot enough to you know to evaporate our flesh, right? But comparison to other stars, very small, very cool. So at the beginning of this lecture, we talked about gas clouds collapsing, right? And usually some kind of gravitational effect happened that caused these gas clouds. That L from clouds always wants to go into the gas and become glass. So will cause these gas clouds to collapse. The first is star formation. The formation of other stars. When nuclear fusion starts, that star, well, we already know the T-Tauri stars will send out energy in the form of their stellar wind. Right? That energy, that push, can trigger other gas clouds to collapse. Right? When nuclear fusion begins, there's going to be, I wouldn't say an explosion, but a burst of energy that travels outward throughout the solar system. That pulse of energy could trigger nearby gas clouds to collapse. Right? When stars die, right, smaller stars eject shells of gas. That moving shell of gas could trigger collapse of other gas clouds. When larger stars die, they go supernova, or this is actually pronounced supernovae. It just doesn't feel right to me to say supernovae. I don't know why. I just like to say they go supernova. Right? Supernovae, I think, is plural. But when a star goes supernova, that is a massive explosion. Shock waves will travel through space-time and disrupt gas clouds and cause a gravitational collapse, possibly. Right? Density spiral waves in our galaxy, right, that are moving through our galaxy if we compress areas of gas and dust and stars, that compression can cause clouds to collapse, right? And gravitational interactions between galaxies. The galaxies, like we've already mentioned before, right, with dark matter out there and whatnot, there's already gravitational attraction that is occurring between galaxies and dark matter. So these interactions in gravity, right, can push and pull on gases, right? And that can trigger an instability, which can trigger collapse, which can trigger a star formation. Excuse me. So let's explain this diagram here. Okay, so let's say we have a large, massive gas cloud in outer space, and we've got some new stars that have formed in them. Okay, and then these stars, they go through their life. Let's say they're massive stars, and they live for a few million years, and then these massive stars, when they end, they go supernova and they explode. Right? This explosion sends energy waves traveling outwards. Right? We create a shock wave. that shock wave collapses gases and condenses them nearby. And along these shock waves, we get gas compressing, forming what we call second generation stars. Right? So these first generation stars are the remains from the supernova. Right? These first generation stars could be neutron stars, pulsars, white dwarfs, or some stars themselves that have not yet detonated. But the shock waves that they create when these stars went supernovae, right, can trigger collapse of other parts of the gas cloud and trigger star formation. Okay, so I'm going to upload this to YouTube, right, and I'm going to try and put it in the correct spot in the excuse me, in on the bright space and in the content. Okay, thank you.